Chapter 5, Measurements of Spirometry and How We Measure Results. In this chapter, we're going to learn about measuring spirometry, reference values, age, sex, height, and ethnicity in spirometry, percentage of predicted, lower level of normal, Z-scores, advantages of using the lower level of normal over percentage of predicted, measurements of spirometry, forced vital capacity, the forced expiratory volume in the first second, FEV1 to FVC, peak expiratory flow, forced expiratory flows, FEF 25 to 75%, and then a full understanding of flow volume and volume time graphs. So at the end of this chapter, you should be able to describe how spirometry results are measured and reported, define and describe reference values, understand the effects of age, sex, height, race on lung function, describe how results are measured against percentage of predicted, define and describe the use of lower level of normal and Z-scores, and then understand limitations of using percentage of predicted and the advantages of using lower level of normal. So at the end of this chapter, you should be able to define and describe each of the key measurements of spirometry, being the FVC, FEV1, FEV1 to FVC ratio, the PEF, and the FEF 25 to 75. You need to be able to recognize each one of these on flow volume and volume time graphs. You need to understand and read flow volume and volume time graphs. Let's start with reference values. So reference values are predicted values against which a child's blow is measured. And reference values are based on equations that take into account age, height, and sex. Reliable interpretation of spirometry results relies on the availability of appropriate reference data to help distinguish between health and disease and to assess the severity and nature of any impairment. The range of values obtained from a healthy population is assumed to represent normal. Unlike many other medical observations, lung function measurements are related to body size and age, where height is a proxy for chest size and age reflects maturity. During childhood and adolescence, growth is particularly rapid, with lung function increasing 20-fold during the first 10 years of life. By contrast, once peak lung function has been attained in early adulthood, this peak being some 5 years later in males at 25 years old than in females at around 20 years old, there is a steady age-related decline in lung function. Height, age, sex, and ideally ethnic racial group must be taken into consideration when defining the normal range for lung function. So what is normal? A vast number of reference equations have been produced studying different populations. The overwhelming number of published reference equations in the past and the differences in the methods of each study complicates the selection of an appropriate reference to use. There were no satisfactory normative data for measurements in preschool children really in the past, and the use of inappropriate reference equations and misinterpretation, even when potentially appropriate equations are used, can lead to serious errors in both over and under diagnosis, with its associated burden in terms of financial and human costs. So to ensure consistency, the reference values should be standardized throughout the population. All of one child's spirometry test results should be evaluated against a single set of reference values, regardless of which reference set is selected. So in the past, there were a variety of reference values used for testing children, and none of them were really ideal. But they were the best option that we had until the Global Lung Function Initiative, that is the GLI, reference values, were published in 2012. So the GLI reference equations are for people aged between the age of 3 and 95 years old. They cover many ethnic groups and have been endorsed by all major respiratory societies. These GLI reference values provide the best, most advanced statistical methods and a globally unified approach to the interpretation of spirometry. So even if results are acceptable and repeatable, if the technician does not select an appropriate reference value for the measurement of lung function, the results of the test and the child's outcome may be compromised. There are two ways of measuring results. The two methods are, number one, the classic older way, which is percentage of predicted. So that is looking at the measured value divided by the predicted value and times by 100 to get percentage of predicted. The new way of measuring or comparing a child's measured values is by looking at a Z-score, which is the measured value minus the predicted value divided by the standard deviation. So in figure 5.1, which is an example spirogram showing the results expressed as a percentage of predicted as well as a Z-score, what you can see in the first left-hand column is the measurements of spirometry. So you see there FEC, FEV1, FEV 0.5, FEV 0.75, FEV1 to FEC ratio, PEFR, FEF 25 to 75%, FEF 25%, FEF 50%, FEF 75%, and then your expiratory time, your time to peak, and your time expired. So the second column, you can see your predicted values. Now, where do those predicted values come from? And the lower levels of normal, where do those come from? They come from your entry of patient data together with your choice of reference value, and that gives you your predicteds and your lower levels of normal. Then you have the best column, which is the patient's actual blow. And then right at the end, the last two columns on the right-hand side is then the second best blow and the third best blow. These are called trial 2 and trial 3. So there you can see that this patient did 3 blows. Now, when measuring these results or looking at the results of the spirogram, we're looking at them from the two columns that say percentage pred and Z-scores. And in this instance, the actual FEC measured by the patient was 1.35 liters. The lower level of normal was 1.13 liters. And this patient had a Z-score of minus 0.44. In the same way, if you were using percentage of predicted to interpret the result, the predicted value is 1.43. The best the patient did was 1.35, and this actual measurement of 1.35 liters is 94% of what is predicted. So you can see in this figure very clearly where the measurements of spirometry are, the predicted values, the lower levels of normal, both of which are derived from the entry of the patient's demographic data, being the height, the sex, and the gender, together with the choice of reference values to give you those predicted values and the lower levels of normal. And then you can see the 3 best blows that the patient did, and then the results expressed as either a percentage of predicted or as a Z-score. Let us look at understanding percentage of predicted values. So where other physiologic parameters like blood pressure or heart rate are not dependent on other physiological properties, spirometry values can greatly differ depending on the child's specific properties like age, sex, ethnicity, and height. So to allow an interpretation of a spirometry test, we compare the known values with the predicted values. And the predicted values are average values of a large population group of healthy children. The software that comes with the spirometer calculates these predicted values for us. So in the ideal situation, spirometry values should be compared to the historical data of the same child. Comparing the spirometry values only with the predicted values can lead to errors. If the FEC and FEV1 were lower than 80% of predicted values, the values were considered to be too low. But if a child has blown 120% of his predicted values and then blows 100% of his predicted values 1 year later, he may have a very big problem, even if comparison with his calculated predicted values shows no sign of abnormality. So even though this child's values are still above normal, if he has lost a lot of lung function in a very short space of time, you might find that there's something going on there. Further, the problem with percentage of predicted values is that you can have a misdiagnosis when fixed cutoffs are used, such as 80% predicted for your FEV1 or a fixed ratio of FEV1 to FVC. In an adult, that would be around 70%, but in a young child, it could be a very young child, 90%, in older children, about 80%. So while percentage of predicted has historically been used to interpret lung function results, Z-scores are far more appropriate because they take into account the predicted value as well as the between-child variability of measurements. So let's then look at the lower level of normal. So the lower level of normal and Z-score is a more accurate way to assess a spirometric value than percentage of predicted. A Z-score is the number of standard deviations a score is above or below a mean. So in the standard normal distribution, the mean is always equal to 0, and the standard deviation is equal to 1.0 reference values. So if you look at this diagram here on the left, figure 5.3, this spectrogram shows the Z-score relative to a normal range, allowing a simple interpretation of the spirometric results. So let's look at it. In the center of the graph, you see a green line running through the peak point of this Gaussian bell curve. This is the mean average for spirometry in a certain age, gender, and height group. So that would be the mean average. And then you can see that to the left and to the right, you have standard deviations below the average or above the average. So in spirometry, the cutoff for normal, the lower level of normal, is a standard deviation of minus 1.64 Z-scores. So these standard deviations are measured by way of Z-scores. So anything below the average of 0 is less than what is expected, and any standard deviation or Z-score above 0 is more than what is expected. So as I said, a cutoff of minus 1.64 Z-scores or standard deviations away from the mean is the lower level of normal when looking at spirometry results. And you can see that on the right-hand side of the graph, everything is colored in green. You have light green followed by dark green. So if a person has a high Z-score, we don't really worry too much about it unless there's consistently high Z-scores over different types of patients in one testing session over one testing day or one testing afternoon, which might show us that perhaps there's a problem with the equipment. But otherwise, if a result is above the norm, we don't worry too much about it. But if the result is below the norm and is definitely less than 1.64 Z-scores, then we need to start understanding that that result would be abnormal. Looking at figure 5.2, this pictogram shows the percentage of the population expected within a certain standard deviation in spirometry. So one standard deviation, there will be about 68% of the population expected within one standard deviation of the mean on any measurement of spirometry. We would expect about 95% of the population within a Z-score of minus 1.64 or plus 1.64. And then we would expect almost 99.7% of the population to be within a Z-score of 3. Advantages of using lower level of normal. So the true lower level of normal, when expressed as a percentage of predicted, varies considerably with age. An FEV1 value of 66% of predicted may be normal in a person who is 80 years old, but it would be abnormal for a person who's 20 years old. Therefore, evaluating spirometry results using the percentage of predicted is very popular, but it should be replaced by the method of using the Z-score. The benefit is that Z-score is completely independent of age, height, and sex. So for example, if the Z-score for any parameter is minus 1.64, this signifies that in males, females, children, adults, that the measured value is at the 5th percentile. So what the 5th percentile means is that 5% of people will still have normal lung function even though they measure below the 100%. In lung function testing, this is regarded as the lower level of normal. So the American Thoracic Society, ATS, and European Respiratory Society, ERS, both recommend the use of lower levels of normal to express between health and suspected disease. At this time, all spirometer software is enabled to report results as percentage of predicted, but not all spirometer software will report results as lower level of normal yet. So only the new software offers results as Z-scores. So in this course, we are going to address the interpretation of spirometry in both ways. We're going to look at it using the older method for interpretation, being percentage of predicted, but always know that the best way to interpret your spirometry results is using lower level of normal and Z-scores. So just a little bit more about the Global Lung Function Initiative, the GLI reference values. In 2012, the Global Lung Initiative published new predicted values that correspond better to the present-day population for spirometry. So for the first time in history, there was a cooperation between 6 international respiratory societies. These were the European Respiratory Society, the American Thoracic Society, the Australian and New Zealand Society of Respiratory Science, the Asian Pacific Society for Respirology, the Thoracic Society of Australia and New Zealand, and the American College of Physicians. So these societies got together and they gathered up lung function of more than 74,000 healthy, non-smoking people spanning all ages and all ethnic groups. And all of these people were measured, and from this vast amount of data, the new GLI predicted values were calculated using very advanced statistical methods. So it is advised that we all use the new Global Lung Initiative predicted values and no longer use other sources of predicted values, so that everybody across the globe is using one standard reference value for measuring spirometry data against. So in contrast to adults in whom there is a steady age-related decline in lung function, which is often accelerated by disease, absolute lung function increases during childhood with substantial changes in the pattern of lung and airway growth during puberty, such that lung disease may represent as a reduced rate of lung growth after allowing for the effect of age and bodily growth rather than an absolute decline in overall lung function. Identification of clinically relevant changes over time in children with lung disease is therefore dependent not only on availability of suitable reference values, but on knowing the expected long-term variability of lung function in healthy children of similar age. So it's well known that pulmonary function differs between ethnic groups, and the importance of adjusting for ethnicity has been emphasized. For a given standing height, non-Caucasian men on average have longer legs than Caucasian men and a correspondingly shorter trunk size and therefore slightly smaller lungs, explaining most of the differences between predicted values for Caucasian and non-Caucasian men. So when a population shares an environment, social customs, diet, and a large number of genes, it is likely that their lung function will be similar as well. This is the basis for ethnicity-based reference equations, but environment, diet, and genes are rapidly changing and mixing, making ethnicity a complex determinant of lung function. So this can make selecting appropriate ethnicity-based reference equations very difficult. Most spirometers will correct or adjust for race. To enable the spirometer to make this correction correctly, the technician must select the race of an individual as well as indicate their age, sex, and height correctly. How race or population is determined varies, and all designations of race or ethnicity are based on self-report from the child or from the child's caregiver, and you should then choose the racial ethnic group that characterizes them best in the software of the spirometer, and this includes biracial or multiracial individuals. So it may be difficult to determine whether to apply a correction factor if the individual is of a mixed ethnic background and their exact ethnic group cannot be determined. In this instance, interpretation and the final interpretation decision will take this into account. So if a correction factor is applied, this must be reported and must also be consistently applied in subsequent tests in the same individual child. So let's just look now at the various factors that affect lung function. Let's look at age first. So lung function increases rapidly with growth during childhood and adolescence and reaches a peak sometime between the ages of 18 to 35. From that point, lung function will slowly decline even in healthy people. So volumes and flow rates tend to increase until about the age of 20 or so and then decline thereafter. A subject's date of birth is usually used to determine their current age, and this, of course, is another opportunity for a manual entry error by the technician when conducting the spirometry. So commonly the error occurs when maybe today's date is entered instead of the subject's date of birth, the technician's not thinking clearly. Or what can happen is there can be a little bit of finger trouble and the decade may be entered incorrectly. So for example, instead of entering somebody's date of birth as the 2nd of the 9th, 1986, the technician may make an error and enter this person's date of birth as the 2nd of the 9th, 1996. So it's helpful after testing to ask the subject to confirm their date of birth when you are checking that the subject details are entered correctly on that test report before the patient actually leaves. Looking at figure 8.5, you can see two example spirograms showing the effects of the incorrect date of birth and age entry into the test results of a spirogram. So in the first example, you will see a spirometry test showing the correctly entered date of birth and age of a 13-year-old individual, with the date of birth being the 19th of April 2006. And if you look carefully then, the predicted value for FVC is 2.56, the FEV1 is 2.30, and then your Z-score is minus 0.43 for FVC, and for FEV1 it is minus 1.18. Now try and keep that in the back of your head. So predicteds are 2.56 and 2.30, and the Z-score is minus 0.43 and minus 1.18. Now when this same child is entered incorrectly as age 3 instead of age 13, look at how the predicted values decrease from an FVC of 2.56 to 1.95, changing the Z-score for the FVC from minus 0.43 to 1.49. And on the FEV1, the predicted when the child is correctly entered as 13 years of age is 2.30, giving the Z-score of minus 1.18. But when the child is incorrectly entered as 3 years old, the FEV1 predicted drops to 1.77. The Z-score is 0.60. So you can see just how much a small error of missing out a 1 instead of a 3 when entering the date of birth can change your interpretation of a lung function test result. Let's look at height on spirometry. So naturally, persons who grow relatively tall also have relatively larger lungs than those who are shorter in stature. So the taller an individual is, the larger his lung volumes and capacities. And like any other manual entry, height can be entered incorrectly for a number of reasons. So the most common reason I've seen for height being entered incorrectly is that instead of entering a height as 157 centimeters, an operator may enter 1.5 centimeters, making a person this tall. And obviously the spirometer does not recognize a human being as this tall, so it may not give predicted values. So also another error that I've seen is that the operator may enter the patient height in centimeters, but the machine may be set up to give the height in inches. So again, you would have some error on your data entry. Another thing that I've noticed is that the height and the weight can be incorrectly entered in the wrong boxes. So instead of entering the height as 157 centimeters and the weight as 63 kgs, perhaps the height will be entered as 63 centimeters, making somebody very short with a weight of 157 kilograms. And again, no predicted values will be given because the computer will not recognize this person as a human being. Another problem with height is the way that height is measured. So if it is measured incorrectly, for example, if a subject wasn't actually measured or was measured with his or her shoes on, or is slouching with feet not against the wall, this can lead to incorrect predicted values. So you need to be very, very accurate when you are measuring height. This is an important part of quality assurance. Look at figures 8.4, which has two spirograms. The one is entering a patient as 153 centimeters and 55 kgs. And the second part of it is where an error has been made on the height, and instead of 153 centimeters, the patient is measured as 135 centimeters. Look at what this does to the predicted values and the Z-scores. So correctly, the FVC should be 2.56 and the Z-score 0.43 on FVC, and on FEV1 it should be 2.30 and the Z-score should be minus 1.18. Look at it when the error has been made. The predicted values drop down from 256 to 193 on the FVC, and on the FEV1 2.30 dropping down to 1.76, substantially changing the Z-scores from minus 0.43 on the FVC to 1.99, and on the FEV1 from minus 1.18 to 0.77. So you can see how a small slip of the finger when entering patient details can make a huge difference to the predicted values and consequently the Z-scores measured on that patient. Let's have a look at the effect of sex on spirometry. So while we know that there are sex differences in early life, prepubescent males and females generally have the same lung function, but post-puberty, the growth of the thorax is greater in males, giving marked differences in lung volumes. So women have on average lungs that are about 20% smaller than men of the same height and weight. Birth sex must be included in the child information, and children should be given the opportunity to provide their sex identity, but should understand also that their sex identity is respected, but the birth sex is the determinant of predicted lung size. If this is not recorded accordingly, it may lead to incorrect interpretation, diagnosis, and treatment of the child. So all of the above factors mean that to optimally interpret spirometry results, you must first know the child's age, height, sex, and race or ethnicity. Knowledge about long-term variability of lung function in healthy children is essential when monitoring and treating those with respiratory disease over time. Spirometry assessments are important both for diagnosing lung disease and for monitoring disease progression and/or response to treatment. While comparison of an individual spirometry result with an appropriate reference or predicted value may identify abnormal lung function, it is often more clinically valuable to assess changes in an individual's lung function following an intervention over time. Now, let's just go on to look at the effects of entering sex incorrectly. Spirometry reference equations are sex-specific, so boys and girls of the same age and height will have different lung function. Males will have larger FVC and FEV1s than females once they are post-puberty. It is easy to make the mistake of entering the subject as a male instead of a female or a female instead of a male. And when this happens, the predicted values will be either over or underestimated. This happens in every workplace globally on a regular basis. By checking this, we can correct any errors in data entry before interpreting the test result. So looking at figure 8.3, we see two example spirograms showing the effect of incorrect gender entry into test results. So the first spirogram, the child is entered as female, and you can see the predicted values are 2.56 and 2.30, and the Z-score correctly is minus 0.43 for FEC and minus 1.18 for FEV1. But when this child is entered as a male instead of a female, look at how the predicted values increase from the FEC at 2.56 to 2.66, changing the Z-score from minus 0.43 to 0.73. And in the same way with the FEV1 when entered as a female goes from 2.30 to 2.32, and the Z-score changes from minus 1.18 Z-scores to minus 1.21. So you can see how, as I say, a very simple mistake when you're entering the age, gender, height, or race of an individual can affect the predicted values, the lower levels of normal, and your interpretation of the result itself. Let's look now at the measurement of spirometry. So there are three key spirometry measurements for a given individual, and they are usually given in raw data in liters and as a percentage of predicted of a reference value, or more appropriately as a Z-score difference from the predicted mean for that person. So the three key measurements are the forced vital capacity. This is the most basic and important spirometric maneuver, which measures the lung size in liters and represents the volume of air in the lungs that can be exhaled following a deep inhalation. So when I'm describing the FVC, the forced vital capacity, I like to think of the four maxes. So the FVC is the maximal volume of air that can be measured with maximal effort from maximum inspiration to maximum expiration. And when the FVC is low, it could mean that the lung is restricted from filling to its normal capacity of air, and that would indicate restrictive lung disease. So in figure 5.4, the example spirogram shows the three key measurements with the results expressed both as percentage of predicted and Z-score in a 13-year-old child. Have a look at it. The FVC is low at 2.12 liters, 87% of predicted, and a Z-score of minus 1.07. Let's have a look at the forced expiratory volume in the first second. So the FEV1 is the volume of air exhaled in the first second of the FVC maneuver, and it's measured in liters. So normally adult lungs generally empty more than 80% of their volume in 1 second or less. The volume is greater in children and less in the elderly. A low FEV1 is the result of a decrease in the airflow through the lung, which may be caused by obstructive lung disease, for example, asthma in a child. The FEV1 is the most widely used of all lung function indices as it is simple and reproducible and can give a guide to the severity of the disease. So looking at the same example that we looked at above, in figure 5.4, if you look at the FEV1 in this instance is normal. The lower level of normal is 1.68. The best value the patient blew was 1.95 liters, which is 91% of predicted, and a Z-score of minus 0.70. The FEV1 FVC ratio is the ratio of the forced expiratory volume in the first second to the forced vital capacity. This ratio is expressed as an absolute percentage and represents how much of the total lung volume, that's the FVC, can be exhaled in the first second. So for example, if the FEV1 was 4 liters and the FVC was 5 liters, then the FEV1 to FVC ratio would be 4/5 or 80%. And what this means is that the individual can breathe out 80% of the inhaled air in the lungs in 1 second. So the absolute ratio is the value used in interpretation. So never look at percentage of predicted when looking at the ratio. Always look at the absolute percentage and the Z-score. This ratio will differ by age. So when it comes to the FEV1 FVC ratio, it will kind of change on a sliding scale from a young child where it can be very high, from about 90%, sliding down as that child grows. Older children, the ratio is approximately 80%, and as they go into adulthood, so that ratio will become lower. Whereas in adults, around about 70%, or in the elderly, even as little as 65%. So looking at the same spirogram below in figure 5.4, in the spirogram, you can see the FEV1 FVC ratio is above the lower level of normal at 91.6%. That's the actual ratio, not the percentage of predicted. And this is 105% of predicted and a Z-score of 0.61. So you can clearly see that in that test result. Let's look at the fourth important measurement of lung function in spirometry. So we're looking at our peak expiratory flow, or the peak expiratory flow rate. And this is a measurement of how fast a person can exhale. This is the maximum rate of airflow attained during the first tenth of a second of the FVC maneuver. So the peak expiratory flow rate is measured in liters per second, and it reflects the status of the larger airways. This is a good indication of child effort and technique. The lower level for the peak expiratory flow rate, like all other measurements, is a Z-score of minus 1.64, or 80% of predicted if your spirometer does not show these measurements. So in figure 5.5, you will see an example of a flow volume graph showing the peak expiratory flow graphically. Let's look at the forced expiratory flow between 25 and 75% of the FVC, and this is the FEF 25 to 75%. So this is defined as the mean forced expiratory flow measured between 25 and 75% of the FVC. It is the average rate of airflow in the middle portion of the FVC. This reflects the status of the medium and small airways and is measured in liters per second. The lower level of normal is equal to or less than a Z-score of minus 1.64 or 65% of predicted. This particular measurement can also be known as the MEF 25 to 75% or the MMEF 25 to 75%. So in some spirometers, this will measure the FEF 25, then 50, then 75%. And in other spirometers, it's the MEF, which is measured at 75%, 50%, and 25%. The flow volume and volume time graphs are the pictures of spirometry, and we looked at that in chapter 1. And we need to be looking at the shape and size of each one of the curves on the flow volume and volume time graphs of the child's actual blow. So looking at figure 5.7, this is an example of a real-life flow volume and volume time graph. So what you can see is the gray dotted lines showing the upper and lower levels of normal, followed by the child's actual blow. And you can see that this child's lung function is below the lower level of normal, which is the smaller of the two gray lines. So there's a loss of volume, and the way the air is flowing out is not as free as it should be. So this brings us to the end of chapter 5, and we'll finish off quickly with some did you know questions. So reference values is the preferred term used to describe normal spirometric values for any individual. Reference values for spirometric measurements are dependent upon a person's age, gender, and height. Correction factors for ethnicity may also be applied. The separation of children, adolescents, and adults is artificial and leads to disjointed predicted values at the transition from adolescence to adulthood. Differences in predicted values between reference equations can be very large. There are more than 300 published reference equations for spirometry, but we are wanting to use the GLI reference equations. The expected lung volume is most affected by height. The taller the individual, the larger the lung function will be. African Americans have lung volumes approximately 10% lower than Caucasians, and Asians have lung volumes 2 to 8% lower than Caucasians. See the two spirograms in the following slides that show how results can differ using the percent predicted versus the lower level of normal for measuring results, and the extent to which ethnic differences in lung function are associated with genetic ancestry as opposed to environmental exposures, nutritional or social economic circumstances remains controversial, with interpretation compromised by the paucity of appropriate high-quality data. Although some groups have suggested that the same ventilatory function predicts the same level of mortality in different ethnic groups, thus discouraging the use of ethnic-specific equations, and others have reported that African genes are associated with lower lung function and that differences in socio-economic circumstances explain only a small proportion of ethnic differences. This brings us to the end of Chapter 5, and soon I'll be meeting you again for Chapter 6.